Hey guys, it's Mr. Sheeline here, back by popular demand. We're going to walk through how to answer number 5 from the Check Your Understanding. Okay, so let me get this set up a little bit better. Okay, so some of the things that you may need, because this is going to branch off of making vectors, drawing vectors to scale. So as you can see here, I've taped together two full sheets of what's it called here, of notebook paper. I've taped them here, making sure that I keep all the lines, pretty much right on spot and all lined up. Okay, and yeah, because it's going to be a big one, or at least how I'm making this. So this is the problem from number 5. And for the most part, it's the chickadee problem. It's the one that the chickadee, walks at a 33 degree angle, walks 22 meters in this direction from the post to, I think, the barn, and then it walks 11 meters. It turns around and then it walks 11 meters from, I think, the barn or whatever the B stands for, to the fence post. I think it's the fence post, whatever it is, or the feeder. I think it's the feeder. Sorry. And we've got to figure out what the displacement is. So, okay. So more or less, when we are working with two vectors, and especially two vectors that are on, two different planes, and for the most part, after we've drawn our resultant here, after we've drawn our, I guess in this case just resultant, we have an obtuse obtuse triangle, and we could solve this with the laws of law of cosine, law of sine, and all that good stuff for the most part. But what I want to do is there's still some information that we don't know about that we need in order to solve this. And if we don't know the law of cosine, we don't know the law of sine. There are some, albeit longer versions, but some decent versions on how to, or strategies I should say, where we can solve for this. So let's solve for this, guys. So this is all the information that we need, or that we're given, sorry, and for the most part what we need. There isn't a lack of information here as far as getting this going is concerned. So let's now get going. So what do we do? So when we're working with triangles and we're trying to make a whole bunch of different right triangles, we have to break these down into squares and also triangles, because we're trying to find something that isn't on our on one of our bearings. It's not on the east bearing, it's not on the north bearing, it's not on south, it's not on west, it's on an angle itself. And so we've got to solve for that angle. Well, how can we do that? Well, the way that we do that, again, we've got to break these into smaller triangles. Now, hopefully if just by saying that, hopefully you can maybe see like, oh, now I know what to do. Oh, yes. I hope you're at that point. But if not, well, let's just for our starters, let's make this our triangle. Let's put it into a square. Okay? Let's just put this guy into a square. Now, I've already drawn this line down here, which is perfectly straight. And I've already got this line up here ready to go, which again is also perfectly straight because I'm using this red line up here as my guide. It's the equal distance up here. So now what I've got to do is I've got to make sure that everything else is equal distance, and what's called in carpenter, the way carpenters call it, they call it plumb. Everything's like more or less squared and equally measured. So we're going to just make this as equal as possible. And we're going to just make it into a square. Okay, do that, and then we're going to come over here. We're going to do the same thing, but we got to make sure we continue this line right here. I'll try this to the best of my ability. Okay. Okay. All right. Now, please, by the way, just in case, and because I haven't really made this terribly obvious, But when I do these kind of videos, make sure you guys are following along with me, like making this yourself. So if you haven't made this, either sketched it or haven't made it by, or made it to scale yet, please pause the video here and go do that, because that's super important, because it doesn't help you if you just sit here and watch and listen. What does help is when you do it for yourself. Okay? Okay. So now we just got to get this box, yeah. And now you can see, here's our original triangle, which maybe in hindsight I should have made a different color, which I can do right now, just so it stands out a little bit better. Okay, so that guy's, black and red. Just so it sticks out a little bit better. Okay, so again, and these are to scale. This is to scale, and my scale is, sorry if I didn't make it obvious, my scale here is 22 meters is equal to 22 centimeters. 11 meters is equal to 11 centimeters. Okay, so I've got that right there. Okay, all right. So we've got this guy confined to a square now, and hopefully you're starting to see what I'm doing here. Okay, because notice this is what we're solving for. Okay, this is what we're solving for. But look, now the thing we're solving for, it itself is now part of a right triangle. And hopefully we can see now, we're going to be breaking this down, in different ways, which we are. So let's just start, let's start slow, and let's just solve one triangle at a time. So let's maybe look over here and we say, like, well, we've got to know the distance over here, okay? We have to know that distance. And if we look up here, we can see that, well, maybe that, that distance isn't terribly obvious. Maybe it is, just by looking at it. But we need to know this distance, okay? We need to solve for this guy right here, so we'll just put like maybe x, I don't know. We have to also solve for this angle down here, okay? We've got to solve for that guy. And we've got to solve for this little y right here, I'll say from here to here, right? We have to solve for here and to here. Got to find that angle so that we can then solve for this distance. Okay, and maybe we really don't have to solve for both of these, depending on how you do this, because you can do it without needing both of them, but for the most part, we should have them. Okay, so now to continue. Okay, so let's just start for right now. Let's just start and focus in on this triangle up here, because we've got a lot of information in this triangle up here. So let's just kind of replicate them over here in the little spot that we have for our work. Oops, and I gotta move some stuff, sorry. I moved some stuff. So let's just kind of focus in on this triangle over here again. Okay. So let's replicate them. So we're going to do this. We're gonna go whoop, show whoop, and then a whoop-bang. Now again, this is just a quick sketch. So we know the hypotenuse here, and the hypotenuse of this triangle is going to be h is equal to 11 meters, and we've got an angle in here. So we arguably we need to solve for, I'd say this side. We should solve for just both sides. Okay, let's just do that. So to solve for both sides, okay, let's solve for that's x and y. Okay. Or this will be, because this is our angle here, okay, if that's our angle, we'll say, and this is what we're using to get them, we'll say that this is the opposite and then this is adjacent, okay? So we'll do that, and we're going to solve for the opposite and the adjacent. So, okay, so to get the opposite, that's going to be so, okay, so that'll be so, and that's going to be the sine of theta is equal to opposite over hypotenuse. And maybe I'll close up on that. Okay, so sorry for large hand here. Okay, but let's start solving for that, because we've got theta and we also have hypotenuse. We're just solving for that guy, so we're going to put the h and multiply it against our sine. So then it's going to be opposite is equal to the sine of theta times our h, which is going to be sine of theta, which is 28, times h, which is 11. And our opposite here is going to be, okay, our opposite, let's see here, sorry, I thought I had this prepared, didn't, times 11. Okay, it's going to be 5.16. Now in this case, just because I know that there's going to be a lot of different sides that we're working with here, we're going to keep sig figs. And I know I've talked about where we don't have to, but just to keep things consistent, especially with the answer that's been provided to you guys, I want to keep this as consistent as possible. So we're going to say that this is 5.2, because I get 5.16. So we're going to do 5.2 meters. Okay, so this is 5.2 meters. I just wrote 5.2 meters up in the up here in the triangle. Okay, so we've got that. So now we can then solve for, below this, we can then solve for our adjacent, which is going to be ka, which is cosine of theta, is equal to adjacent over hypotenuse. Going to do the same thing we did up here. So then it's going to be adjacent is equal to, and I'm just going to solve for it, okay? This time it's cosine, so then the adjacent is going to be 9.7 meters, okay? So that means our x up here is 9.7 meters, okay? Now we can add that to our big boy over here. So this guy right here, so from B here to right here, this is 9.7 meters. And then from here to F, that is 5.2 meters. Now, let's say you're skeptical of that. Let's just say, for instance, well, if you're skeptical of that, oops, and I need to, my aspect ratio is off. If you're skeptical of that, you can just use a ruler. Since everything's to scale, well, let's just see what we get. And it looks like, let's see, I get closer to 5.3, but I'm not too far off. It's like 5.26 or 7 is what I get to right there, okay? Which is, so we're pretty much, we're golden there. Well, let's see what we get here. Looks like I'm going to get, I get 9.7 smack on the dot, okay? Yeah, give or take. Yeah, give or take. So I get somewhere between 9.6 and 9.7 on my ruler. So we're in good shape so far, okay? So what else can we do? Okay, so we've got that, okay? So we could now, or what we should do now, sorry. What we should do now is that we should now recognize that, oh, we've got this distance. Well, why don't we find this distance too? You may ask yourself, why do we want to do that? Well, again, we've got a rectangle here. I think I said square earlier, but we've got a rectangle here. Well, we should know then that because these are all, this is a right corner, that's 90 degrees, that's 90 degrees, that's 90 degrees, and that's 90 degrees, okay? We should know that, oh, the distance between this point and that point is going to be the same as the distance between this point and this point. Oh my goodness. So if we get this guy up here, and then we add that to that, we then find our x down here. And then all we have left to do is then we've got to find this y, okay, which we'll get into in just a smidgen here. So, okay. So let's now take a look at this. Oh, and then, yeah, we'll get to that in just a bit. So let's take a look at this. So, all right, so we're going to find this side right here now. So let's find that side. So this is going to be, we're going to draw this over yonder, okay, give or take. Okay, so this is the information we have. So the hypotenuse on this guy is going to be 22 meters. Okay, I'm going to shimmy this on over. So it's going to be 22 meters. Okay, and if we look at our big guy here, actually before we start doing that, if we look at our big guy over here, so, okay, because we know that this whole entire spot right here is 90 degrees, okay, we've got 33, that leaves this angle right in here, that leaves this angle, 90 minus 33, what do you think you're going to get? That's right, children, you get 57. So we've also got the angle, which is really, really cool. Okay, so then we can transfer that information over here. Now I got to move my thing. We can transfer that over to here to where we've got an angle of 57 degrees. Okay, and we should have enough now, information now, to find this x-axis up here. Because we really don't need to find this. You can if you want. Actually, probably wouldn't be a bad idea. That would make things a whole lot easier. Actually, let's do that, because we'll do the same thing that we're doing at the same time. Okay, and I'll explain that when we get there. So actually, we will find this. Okay, so let's find x first. Okay, so x we're going to use, because our angle's down here, okay, that's going to be opposite. So x this time is opposite, while our y over here is the adjacent. Okay, so we're just going to use, so for the x, so sine of theta is equal to opposite over hypotenuse. And so just because we've already done this, our opposite in this case, so it will be, because remember we're going to multiply the hypotenuse against the sine. So that's going to be 22 this time times the sine of 57. And what we get is 18. We should get 18 meters for our opposite. So this is 18 meters. Okay. Because again, remember, and also we're keeping sig figs. That's why we're just to keep things nice and easy here. Okay, so we get that, and then our y is going to be the cosine, of course. So it'll be ca. So it'll be cosine of theta is equal to adjacent over hypotenuse, and so our adjacent here, that's going to be cosine, it'll be 22 times our cosine of 57, and that's going to give me 12 meters. Okay, 12 meters. I get 11.98, so we'll keep it 12 meters. Okay, just to keep sig figs. Okay, so then we're going to put that up here. So this is going to be equal to 12 meters. Okay, nice. So we've got that. So let's now transfer that to our big picture. So that means from here to here, that is 18 meters. Okay. And then this guy over here, that means that my distance over here is going to be, what did I find? I found 12 meters. Okay, and again, let's say we're skeptical of that. Well, let's just double check. Okay. So using my ruler, I'm going to measure that. And it looks like my physical measurements are a little off. Or maybe I don't remember exactly. What did I get? Maybe it doesn't. Let's see, sine. So I got 18.45 is what my full answer was. And if I look at my measurement here, I'm pretty spot on with 18.45. It's more 18.4 on the dot is what I get. But that's pretty much spot on. Okay. And then again, over here, we want to double check. We can measure. And again, I got like 11.98. And I'm looking closer to just 12 even. Okay. So, but again, I'm pretty much right on the money as far as drawing things to relative scale and also keeping sig figs. Keep that in mind too. Okay. And that's why when I talk about, like, we could have just easily found the displacement already and called it a day. But remember, we just want to double 100% make sure that our calculations are correct. And really, we should be going more off of calculations than this. In this case, just because we want to practice the calculations more than just, drawing the pictures. Okay, so what does that tell us? Well, that kind of tells us that maybe we didn't need to solve for this guy right here, which, okay, fair enough, that's fine. But we did absolutely need to solve for this. So and not only did we just solve for both of these to find the total distance, which, by the way, is going to be down here, which 18 plus 9.7, that's going to give us, that's going to be 27.7, so x down here is just going to be 28 meters, okay? So, but not only did we find that, but if we notice over here, same idea that this to here is the same as this to here. This to here is the same thing as this to here. Okay. So actually we did need to find this actually. So we know it's 12 over here. Okay, the whole distance is 12. We found 5.2 over here. So 5.2 minus 12, okay? So 12 minus 5.2, that means our y here is 6.8 meters. So now we have two sides to a triangle that where we can now solve for the angle down here, and we can also find the displacement in the beginning, okay? So let's do that. In this case, where to fit all that data in? We're going to try to fit it in over here. Okay. Kind of squish it in over here. So here's my new triangle. So I've got 28 meters here, 6.8 meters here. I'm trying to solve for this guy, and I'm trying to solve for theta here. Okay, because this is now we're getting to what we want in our calculations. Okay, so in order to find this, we're only given two sides, so we have two options. So either we can go for theta and then use, SOHCAHTOA in order to find our hypotenuse, and or we can use Pythagorean's theorem, a squared plus b squared is c squared. So let's just see what Pythagorean's theorem is going to give us. Okay, so Pythagorean's theorem, it's going to be 28 squared plus 6.8 squared is going to be 830.24. We're going to find the square root of that, so 830.24, and we get something like 28. So Pythagorean's theorem, we get 28.81. We'll just keep it at that, okay? That's what we should be looking for here, okay? So let's see if that's how good that is compared to finding theta and then finding that, and then also match it to our measurement on the picture there. So let's now we're going to solve for theta, but to solve for theta we've got to use tangent and SOHCAHTOA. Opposite, so opposite over adjacent, so that'll be tangent of theta is going to be opposite over adjacent. Okay, I'm going to solve this because I need to solve for theta, because remember, we got to now make that the inverse. So that's going to be inverse tangent with opposite over adjacent, which you can plot that into your calculator yourself. So inverse tangent, and the opposite is going to be 6.8 divided by the 28, and we get for our theta here, and remember keeping sig figs, it's 16 or 13.65, so that's going to be 14 degrees. We're going to keep that easy, nice and easy, 14 degrees. So now that guy is 14 degrees. Okay, so now we got to solve for our hypotenuse. So now that we've got theta, we have choices. Either we can use, we can use sine, we can use cosine, doesn't really matter. Okay, let's just use sine, just because, it's the first one I thought of. So sine of theta is equal to opposite over hypotenuse, SOHCAHTOA. And then we're solving for hypotenuse, and remember we just switch them. So our hypotenuse, let's see, that's going to be the opposite, which is going to be 6.8, divided by the sine of 14. And we get something that's a little different. We get 28.1 meters, okay? Which I understand I understand that the answer is 29 meters. And this kind of shows it right here, and we'll also show the actual physical one. But we're just gonna go with our mathematical calculations here, and we're going to say 28 meters. Okay. All right. So now we just found the displacement. We just found it. Okay. So now we can add that over here. So now our displacement is 20. We're gonna say 28 meters. Again, I know the answer says 29 meters on the video, but we're going to go with 20 on the YouTube description, or the description for the video that's on YouTube that you watched the other day. But we're going to say it's 28, and I'll explain why we got 28 and not 29 here in a bit. So we're going to say it's 28, okay? And now we've got to make sure, now what we have to do is we have to identify this properly, because it is a displacement. And remember, displacement cares about direction. So we've got to now figure out what our direction is. Well, we found the angle in here. Oop, I'm going to move my paper. We found the angle in here earlier, and it's 14 degrees. Okay, now why is that important? Well, it's important because of this factoid right here. It's important because this angle touches one of our main bearings, because this is east right here. Okay, this is east, this is north, and we can't, unfortunately, we can't use this angle right here. Okay, we just can't use them. Now we can see though that that's going to be 19 degrees, but unfortunately we can't say that's 19 degrees in this case. You try to explain to me that angle. What do you say? Is it 19 degrees north of east? Is it 19 degrees east of north? You tell me. Okay? You can't. That's the point. You can't tell me that's 19 of anything. Okay? Because it's stuck. Both angles here, or sorry, both faces of the triangle here are both not touching a main lead bearing. Okay? A compass bearing. But the 14 degrees is. And specifically that 14 degrees, because it's opening, up away from east in the upward direction, that means that our direction here is going to be 14 degrees north of east, just like we have in the answer. Okay. All right, good. So now basically the last thing we have to do now is we got to solve for average velocity. Well, we know that average velocity is going to be displacement over time. And we know displacement, so we know that displacement now is 28 meters. Or we're going to keep, remember, we're keeping it 28, and I'll explain why it's 28 here at the end. And then time, and if we look back at the question, I've already forgotten the amount of time it took. If you've already got it, you've already got it. Let me check here. But this took 4.4 seconds. 4.4 seconds. So we just plug in our values here. So it'll be 28 over 4.4. And we should get an average velocity of, give or take, we're going to say 6.4, which again, I understand is different from the answer that we got. Okay. So, because the answer the answer that we should have had was 6.6. Okay. And then before we leave this the way it is, because that's not done yet, okay, we're going to write it up here, meters per second. We also have to attribute the same direction, the same vector as we did for the displacement, because it's a vector quantity. So it's 6.4 meters per second, 14 degrees north of east. Okay, and then before I get into the whole 28 meter debacle, why is it that we used the full time, but we didn't use the distance to find the velocity? So remember, velocity is a vector quantity. We care about direction, okay? And when we care about, in saying that, we're using displacement. And remember, displacement only cares about where you started and where you ended. So in this case, we only care about, the fact that we started, here, I'll try to get this whole thing on the screen. We started here and ended here. That's all we care about, okay? It's fine if they went 22 and then 11, but we need to know, well, what's this? Cutting from here to here, what is that? And how long did it take for them to go from here to here? So that's why it's the total time. That it took to go from, here to here, even though they actually went like boom, boom, okay? So we use the total time, and we use the displacement rather than the total distance, okay? So that's why, and that's what we're going to be doing. When we ask for average velocity, you're going to be using this bad boy right here, okay? But there will be questions where you're going to have velocity here and you'll have velocity here. But same idea, you're going to find average velocity this way, okay? Now, why is it that we got 28 meters instead of 29? And not just 28 meters, and not like 28 meters, like 28.5. We got 28.1 meters. How did we get 28.1 meters? And what it comes down to, what it boils down to, is the fact that we had to keep sig figs. So because we had to keep sig figs between the degrees, or at least, again, And I know that's confusing because I've told you guys that you don't have to keep sig figs in my class. I just did to keep things nice and easy, just so we're not going back and forth from 2 to 3 decimal places. But we got 28 meters because of the fact that we kept things at two sig figs. Because this guy should arguably not be 18. It should be like 18 point. I think it should be like 18 point, like 4. The 9.7. I mean, that should be 9.7. 5.2 should be that. The 6.8 arguably should be more of like 7 even. And we can double check that. Like it should be. No, that's actually, never mind. That's the wrong side. Oh, this side, the 12. The 12 should be like 12.2. You know, so we're losing some values. We're losing some measurements as we go along when we keep sig figs to just 2. So that's why we end up with 28. And also, all, you know, the degrees here, 57 is fine here, but this is more like 14.4 degrees. What else? Again, because we lost some value in our measurements, by the end of it, when we had to find this final line here, it then turns it into 28 rather than 29. Okay, so how does that compare then to our actual measurement? Well, let's see. So let's line this up. So I'm lining it up. It looks like I'm looking right now at something that is way more accurate to our Pythagorean theorem number. So this is what I got. So that, remember, that is this squared. It's going to be the 20. It's going to be this squared plus this squared, and then taking that sum and then just finding the square root of that sum, and you get this. You get 28.81. So let's now look at my ruler and where it lines up at. You tell me. We're pretty much golden right there, man. That, it's going to be, let me double check the other end. Yeah, that right there, from as best as I can make it out, the angle of the camera is a little off, so it looks closer to 29 from your guys' perspective, but from my perspective, it's like 28.9, like on the mark, which is pretty much spot on. Okay, and that's how we get the answer 29. And then on top of that, when I did this last year, when I put the answers together last year, I didn't keep sig figs, and so again, I just kept sig figs so it wasn't as messy and unruly, I guess, when I was doing the calculations. Now, so then you must ask yourself, well, Mr. Sheeline, what if in a question like this I get 28 but the answer on your key is 29? Are you going to mark that wrong? I'll just say that I wouldn't mark it wrong if I see the work. So if I see the work and I see that you did, like, let's say you did everything that I just did, and if you did all the work and you put in the time and you put in the effort to show like how you got that value, no, I wouldn't, 100% I would not mark that wrong, as long as the process was correct, obviously. And I guess that meaning, and that means that if I see like you clearly have no idea what you're doing, and you may have just guessed, there may be some points that are taken off. Well, it's a case by case basis. We'll just say that. So, but anyway, so no, I wouldn't mark that wrong. If you did all this work and you showed me how you got that answer and you're off by a figure, no, I'm perfectly fine with that answer. But if you were to get something like 25, or if you were to get something like 32, then I would be like, I'd mark some points down. I'd be like, we're kind of off here. That's not, we're missing something somewhere. We're doing something wrong somewhere. We've got to go back to see what's going wrong. Okay, so all right, guys. So that right there is pretty much like when in doubt, like especially when we've got all these different kind of vectors that are going each their own ways, and it's hard to make to get a compass on them, put a box on it, okay? Like what we did here. Make as many boxes as you can, and try to make as many right triangles as you can to solve for those sides. It is a lot of work. Like, I get it. It's a good amount of work to do this, but this practice is great. And I can tell you from my personal experience, like doing this, and I mean, being in construction, this also just helps and makes more sense to me. But over the summer, I've been doing a project of finishing out a basement, and doing this, just being cognizant of not just being cognizant of angles, being cognizant of sides, making sure that everything's square, everything's plumb, everything is exactly the measurements it's supposed to be. It's really helped me to finish out the basement properly, and inversely, doing the basement has also made me better at doing this and just being more accurate. At least as accurate as I can be within a given moment. But anyway, so that's how we solve for this guy. If there's any other questions, if there's any other check your understandings you want me to do, you want me to walk through, just please let me know. Maybe I can make another video, whatever it is. And I know this one ran pretty long, but as you can see, there's a decent amount of work that had to go into it in order to solve for it. So again, if you have any more questions for me, please let me know. If not, then I'll see you in the next one.